Welcome back to the deep dive. Really excited about today's topic.
Me too. It's a big one.
Yeah, we're plunging into something super critical for, well, basically the future of AI. We're talking about architecting high performance, large language model inference systems. Our mission here really is to give you that shortcut. We've sifted through a ton of expert stuff, technical reports, architecture guides, and we're pulling out the key nuggets for you so you can quickly get your head around this pretty complex world of making LLMs run fast and efficiently, in the real world.
Yeah, and it's really important to see that LLM inference, especially when you compare it to training, throws up some unique and really tough engineering problems. We're not talking about lab experiments here.
Yeah.
These are live online services where latency is king.
Hmm.
They need, frankly, ruthless efficiency to actually work for users.
Exactly. Ruthless efficiency. I like that. It's not just getting an answer, it's getting it now for potentially millions of people at once and, without costing the earth. So we're going to peel back the layers, look at the basic architecture, the key tricks for optimization, how these things are built to scale up. It's a really fascinating look at how engineers are tackling some incredibly tricky problems. So to start us off, what are the absolute bedrock pieces? What makes up one of these systems?
Okay, so at its heart, you've basically got three main parts working together, almost like a specialized production line. First up, you have the API server, or maybe call it a router. This is what the outside world talks to. It handles the incoming requests, checks they're valid, does rate limiting. Sometimes it even manages the continuous batching logic we'll get into. And these are often built in really high-performance languages, like Rust, just to minimize any overhead right at the front door.
The front door. Got it. What's next down the line?
Next is the query queue and scheduler. Think of this as the air traffic controller. Central Command, its main job, and it's crucial, is to decouple the crazy rate of requests coming in from how fast the GPUs can actually process them. So it holds on to pending requests and then smartly groups them into optimal batches. Keeps the GPUs fed, but not, swamped.
Right. The buffer and the brains deciding what runs when. Makes sense.
And the third piece.
And third is the inference engine. This is the powerhouse, the heavy lifter. It gets those batches from the scheduler, manages the model weights, and the really important key value cache that's like the model's short-term memory for attention. And it actually runs the calculations, the forward passes on the GPU to generate the tokens. And these engines are usually designed to be modular, so you can swap bits out as things improve.
So a sophisticated line, API server, queue scheduler, inference engine. You mentioned bottlenecks earlier. Does one of these usually cause the most trouble? Or is it, like, all over the place? That's a great question. It definitely varies. Often the inference engine is the pinch point, especially around memory, like that KV cache I mentioned. But honestly, if your API server can't keep up or your scheduler's making bad batching decisions, you can starve even the fastest GPU. Yeah. It's really a system where, every link in the chain has to be strong.
Okay. So we've got the components. Now, reading through our sources, there's this one concept that just kept coming up, described as maybe the single most important thing for inference performance. Can you walk us through this prefill and decode dichotomy? Why is that so critical?
Ah, yes. This is absolutely fundamental because it splits the generation process into two really distinct phases, and they have totally different performance characteristics, different bottlenecks. So the prefill phase, this happens right when a new request comes in. You take the whole input prompt, maybe hundreds of tokens, and process it in one big go, one forward pass. This part is compute bound. Its speed is limited by the raw number crunching power of the GPU, the FLOPS. And its main job is to fill up that key value cache.
Okay, prefill, big calculation, compute bound, fills the cache. What's the other phase?
That's the decode phase. This is where the model generates the response, but it does it one token at a time, auto-regressively. Now, for each new token, it needs to do a forward pass, but reuses the attention information stored in the KV cache from the prefill and previous decode steps. And this phase is memory bandwidth bound. It's limited by how fast you can shuttle data, especially that KV cache from the main GPU memory HBM to the faster on-chip memory, SRAM. You have to read that cache for every single token.
I see. So one big compute hit, then lots of smaller memory hits.
Exactly. And the really big implication, the kicker, is that the KV cache itself takes up a huge amount of GPU memory, often way more than the actual model weights. This just makes that memory bottleneck in the decode phase even worse. So this split, this Prefill Decode thing, it changes everything about how you optimize. It's not just go faster. It forces you to fight this really tricky battle against memory limits, especially during decode. It's like playing high-stakes Tetris with GPU memory. Every megabyte counts. Memory Tetris on a massive scale.
Yeah.
Love it.
And that's exactly why we see all these clever optimizations pop up. Things like page attention to manage that memory better, or model changes like MQA or GQA specifically designed to make the cache smaller. It all stems from this dichotomy.
So if it's a game of memory Tetris, how do we keep score? How do we know if a system is actually high performance? What are the metrics that matter?
Right, good question. You need a mix of latency and throughput numbers. For latency, a key one is time to first token, or TTFT. That measures how long from the request hitting the server until that very first word of the response appears. Super important for making things feel, snappy, like a chatbot responding instantly.
Okay, TTFT for responsiveness. What else?
Then there's time per output token, TPOT, sometimes called intertoken latency, ITL. This is the average time it takes to generate each subsequent token after the first one. This tells you about the streaming speed. Is the text flowing smoothly, or is it like drip, drip, dot, drip? Nobody wants a slow drip.
Definitely not. So TTFT and TPOT for latency. What about overall speed? On the throughput side, you look at tokens per second, just the total number of tokens the whole system is spitting out. And also, requests per second, how many user requests are actually getting completed. But arguably a much better, more practical metric for production systems is something called goodput.
Goodput. Okay, tell me more.
Goodput measures the maximum throughput, say, request per second that your system can handle while still meeting your latency targets, your service level objectives, or SLOs. So you might define it as like the max request rate where 90% of requests have a TTFT under 200 milliseconds and a TPOT under 50 milliseconds.
Right.
It forces you to balance raw speed with the actual user experience. Benchmarking needs this. You have to test with realistic, spiky workloads, maybe using tools like GenAI Perf, not just find some theoretical max tokens per second in a lab.
That makes so much sense. So if I'm building an LLM product, maybe for a startup, focusing on goodput, not just raw speed, that's like the key mindset shift for production.
Absolutely.
Yeah.
I'd say so. Raw tokens per second might look great on a slide deck for your engineers, but goodput is what actually keeps users happy and, paying the bills. It forces you to optimize for what matters in the real world, not just some peak number that ignores whether the user is having terrible time waiting.
Okay, fantastic. We've got the blueprint. We know how to measure success with things like goodput. Now, let's get into the engine room. The real secrets to making these things efficient. How do we actually achieve that ruthless efficiency? Let's talk about advanced scheduling and batching first.
Right. So the old way was often static batching. You wait for a full batch of requests, run them, wait for them all to finish, then start the next batch. This leads to a lot of wasted GPU time while waiting, and also head-of-line blocking, where one really long request holds up everyone else behind it in the batch. Not great.
Yeah, sounds inefficient. What's the fix?
The big improvement is continuous batching, sometimes called in-flight batching. Here, the scheduler works smarter, more dynamically. It operates at the iteration level, basically token by token. As soon as any request within the current batch finishes generating its output, boom, it's evicted. And immediately, a new request waiting in the queue can be pulled into that now free slot in the batch. This keeps the GPU way busier, boosts throughput massively, and cuts down wait times.
Ah, much more dynamic. Keep the GPU fed constantly.
Exactly. But just filling batches isn't enough. You need intelligent scheduling too. Trying to run the shortest jobs first usually reduces overall wait times, but you don't know how long a response will be beforehand, right?
Yeah.
So people use learning-to-rank schedulers, or LTR. These use tiny, fast predictor models to estimate the likely output length for incoming requests. Then they prioritize the ones predicted to be shorter.
Wow, using ML to optimize the system itself.
Yeah, it's a cool example of ML for systems. It can really help reduce average latency and boost throughput. Of course, you also need fairness tricks like aging, so really long jobs don't just get ignored forever.
That's clever stuff. Okay, intelligent scheduling helps throughput, but let's swing back to that memory bottleneck you highlighted, the decode phase, the KV cache. If that's the Achilles heel, what's the absolute biggest challenge with it, and how are people fighting back?
The single biggest headache with the key value cache is definitely its size. As you said, it's critical. It stores those intermediate attention states so you don't recompute everything for every token, makes decoding feasible. But the problem is, its memory usage can just explode. It grows linearly with its sequence length and the batch size.
Okay.
It can easily eat up more GPU memory than the actual model weights. I remember on an early project, it was just brutal. The KV cache was the only thing limiting how many users we could handle concurrently. It was like this memory monster constantly demanding more VRAM.
Wow, so like Llama 7B, you said, half a megabyte per token potentially. That adds up fast in a big batch.
Exactly. So engineers attack this on multiple fronts. It's not just one solution. First, you have architectural choices in the model itself. Things like multi-query attention, MQA, or grouped query attention, GQA, are designed to share parts of the cache, shrinking its size from the get-go. Or sliding window attention, SWA, like Mistral uses, puts a hard limit on how far back the model looks, effectively capping the cache size.
So bake savings into the model design. Smart. What else?
Then there's better memory management. The big breakthrough here was page attention, which came out of the vLLM project. Think of it like virtual memory in your OS. It divides the KV cache into fixed-size chunks or pages that don't need to be stored contiguously in the GPU's physical memory. This fights fragmentation-wasted gaps between allocated blocks and lets you pack way more requests into memory, effectively increasing your batch size and GPU utilization. Huge deal.
Like virtual memory for the KV cache. That's really cool. Okay,
Right.
architecture and memory management. What else?
Third, you can do cache reduction and compression at runtime. KV cache quantization is a big one, storing the cache values using fewer bits, like FP8 or INT8 instead of FP16. Halves the memory footprint right there, and speeds up memory access too. You also have eviction policies. Techniques like streaming LLMs attention sinks or ideas like H2O or scissor hands try to intelligently figure out which past tokens are less important for the future generation and just discard their cache entries to save space. Keep only the important stuff.
And so dynamically shrinking or compressing it. And the last layer.
And finally, cross-request optimization. The main technique here is prefix caching. If lots of users start their prompts the same way, think of a chatbot system prompt. You calculate the KV cache for that common prefix once, and then reuse it for all those requests. Big savings in specific scenarios.
Wow. Okay, so it's like this whole arsenal, model design, smart memory allocation, compression, eviction, reuse. You really need to combine these.
Yeah, absolutely. There's no single silver bullet. A top-tier inference system is likely using a combination of several of these KV cache optimization techniques.
Okay.
It's a sophisticated dance.
It really sounds like it. Okay, beyond the system architecture and the cache, what about tuning the model itself, or how the tokens actually get generated?
Definitely. Quantization is huge here too, but applied to the model weights and activations this time. Again, reducing the numerical precision FP16 down to INT8, or maybe FP8, even INT4, the benefits are similar. Less VRAM needed, faster memory transfers, which is key for decode, and often faster math on hardware like Tensor cores.
Right, but precision reduction sounds like it could hurt accuracy.
It can, yeah, that's the trade-off. INT8 needs care, maybe techniques like smooth quant, to maintain quality. FP8 is looking really promising as a good balance, good compression, good speed, often minimal accuracy loss because it has a wider dynamic range. INT4 saves the most memory, but usually impacts quality more. This is often done after training, called post-training quantization or PTQ.
Okay, quantization for smaller, faster models. What
Yeah.
else?
Another really cool technique is speculative decoding. This attacks the slowness of generating tokens one by one. The idea is you use a second much smaller, faster draft model to quickly generate a chunk of potential future tokens, say 5 or 10.
Huh.
Then the main large target model verifies that entire chunk in a single parallel forward pass. If the draft was right, great, you accept all those tokens. If it made a mistake halfway through, you accept the correct ones and let the target model fix the next one, then maybe try drafting again.
So draft cheap, verify expensive, but verify in parallel.
Exactly. The big win is that verifying multiple tokens costs the target model roughly the same memory bandwidth as generating one token sequentially. So you get speed up, often 2-3x, without changing the final output at all. It's lossless. It really leverages that asymmetric compute idea. Use something cheap and fast to accelerate something expensive and slow. There are variations like Medusa. Look at decoding. It's a hot area.
That sounds almost magic. Draft then verify? Are there downsides? Like if the draft model is really bad.
Yeah, that's the catch. If the draft model guesses poorly too often, the target model spends more time correcting than benefiting from the parallel verification. So the quality of the draft matters. And maybe for super short responses, the overhead isn't worth it. But for most typical generation lengths, it's a significant win.
Fascinating. Okay. And for the real performance junkies, you mentioned diving even deeper, down to the GPU level with CDA. What's the quick story there?
Right, yeah, that's the lowest level. CA is NVIDIA's whole system for programming GPUs. You write these functions called kernels that run in parallel across thousands of threads. But writing good CEDA is notoriously hard. You're managing memory hierarchies, thread synchronization. It's complex. So key optimization techniques there include things like kernel fusion, combining multiple small GPU operations into one bigger kernel. This reduces the overhead of launching kernels and keeps data in faster on-chip memory, avoiding slow trips back to the main VRAM.
Less back and forth with the slow memory.
Exactly. And of course, making sure you're fully utilizing specialized hardware bits like tensor cores, which are designed specifically for the matrix multiplications common in AI. But because raw CUDA is so tough, we see these high-level libraries like Triton or FlashInfer becoming really important. They let developers write efficient kernels in a more Python-like way,
Huh.
abstracting away a lot of the low-level pain. Huge productivity boost.
Gotcha. So even at the low level, it's about reducing memory movement and using specialized hardware, often via smarter tools. Okay, now let's zoom back out. Models are getting bigger, demand is exploding. One GPU often isn't going to cut it. How do we spread the load? How do these systems scale?
Right, you need parallelism.
Mm-hmm.
And there are different flavors, often used together. The simplest is data parallelism. You just replicate the entire model onto multiple GPUs, then you split the incoming request among them. Great for boosting overall throughput if your model fits comfortably on one GPU.
Okay, multiple copies. What if the model doesn't fit?
Then you need tensor parallelism. Here, you actually chop up the big weight matrices inside the model layers and spread the pieces across multiple GPUs, usually within the same server connected by something fast like NVLink. This lets you run models that are too big for a single GPU's memory. It also helps reduce the latency of a single forward pass because the work is shared.
So data parallel for more requests, tensor parallel for bigger models or faster single requests. What else?
For truly enormous models spanning multiple machines, you use pipeline parallelism. You divide the model's layers sequentially across different GPUs or nodes. So node 1 handles layers 110, node 2 handles 1120, and so on. Data flows through like an assembly line. It increases the latency for the first token of a single request, but boosts overall throughput because the pipeline stays full with multiple requests flowing through simultaneously.
Like a multi-stage factory line.
Kind of, yeah. And then there's expert parallelism, which is specific to these mixture of experts, or MOE, models that are becoming popular. In MOE, you have multiple expert subnetworks. Expert parallelism puts different experts on different GPUs, and you route data only to the needed expert for each token. And in practice, you almost always see hybrid parallelism, combining maybe tensor and pipeline parallelism or data and expert parallelism to get the best trade-offs for a specific model and workload.
Okay, a whole toolkit of ways to distribute the work. This leads us nicely to something you mentioned sounds pretty cutting edge, maybe the future? Prefill Decode disaggregation. What's that about?
Ah, yes. This is a really smart architectural idea that directly tackles that fundamental prefill decode dichotomy we discussed. The core idea is, why run the compute-heavy prefill phase and the memory-heavy decode phase on the same GPU when they have such different needs? Let's separate them. So you create two different specialized pools of GPU workers. One pool optimized for prefill, maybe with high compute GPUs, another pool optimized for decode, perhaps with GPUs that have tons of memory bandwidth.
Separate pools. How does a request flow through that?
A smart router gets the request. First, it sends it to a worker in the prefill pool. That worker crunches the prompt, generates the initial KV cache. Then that KV cache gets transferred, usually over the network, to a worker in the decode pool. And that worker takes over, using the cache to generate the response tokens one by one.
Wow, okay. What are the big advantages of splitting it up like that?
Several big ones. First, specialized hardware. You can use the best tool for each job, maybe powerful but expensive compute GPUs for prefill, maybe slightly cheaper GPUs with great memory bandwidth for decode. More cost-effective. Second, independent scaling. If your workload has lots of long prompts but short answers, you scale up the prefill pool. If it's short prompts but long answers, you scale the decode pool. Much more flexible resource allocation.
Better matching resources to the actual need.
Exactly. And third, improved resource utilization. The compute-hungry prefill phase isn't fighting for memory bandwidth with the decode phase on the same chip, and vice versa. Less interference, better overall efficiency. Of course, this needs more complex infrastructure, things like distributed KV cache management systems, super fast networking like NIXL to move that cache around quickly. It definitely makes the system architecture more sophisticated.
It really sounds like distributed systems engineering meets LLMs. Very cool. Okay, so we've covered speed and scale, but for production, it also has to be reliable, right? What makes these systems robust?
Absolutely. The key pillars here are scalability, reliability, and observability. We touched on scaling, but for intelligent autoscaling, the best practice isn't just watching GPU utilization. Instead, you scale based on application-level metrics, things more directly tied to user experience and load, like the size of the request queue or the average batch size you're achieving. Using Kubernetes HPA with custom metrics like these is way more effective for LLM workloads.
Scale based on demand, not just raw GPU use. Makes sense. What about reliability? Things inevitably break.
Yep. So you need the standard stuff.
Mm-hmm.
Redundancy, multiple copies or replicas of each component, failover mechanisms, maybe deploying across multiple availability zones or even regions. You also need solid state management, especially if you're using things like prefix caching, maybe using a distributed cache like Redis to hold that state reliably. But there's also a more advanced idea emerging called algorithmic fault tolerance, or AFT. Systems like LLM try to leverage the fact that neural networks can sometimes tolerate minor errors. So instead of crashing the whole system for a small, transient hardware glitch, AFT tries to detect if the fault actually matters to the output quality and only triggers recovery mechanisms if needed. Potentially saves a lot of downtime.
Huh. Using the model's own resilience. Yeah, clever. And the last pillar.
Comprehensive observability. Non-negotiable. You need the classic three pillars: detailed logging, rich time series metrics, and distributed tracing. Metrics should cover performance, TTFT, TPOT, utilization, GPU, memory, cost, if tracking cloud spend, and even quality metrics. Tracing is vital to follow a single request journey through that complex, potentially disaggregated system. Tools like Prometheus for metrics, Grafana for dashboards are pretty standard. You can't run these complex beasts blind. You absolutely need to see what's going on inside.
Right, you can't optimize or fix what you can't see. Okay, we've gone deep into the tech, but it's easy to forget these systems are built by people, right? How does the human element fit into this picture, especially with AI itself being part of the toolkit now?
Yeah, that's a great point. It's maybe more crucial than ever. For technical leadership, the role is shifting. It's less about just managing tasks, more about being a true systems architect, navigating this insane complexity. Leaders need to understand not just how to build these systems, but how to leverage AI tools effectively in the building process itself, using AI to help manage AI development, if that makes sense. Plus, championing responsible AI development, of course.
Using AI to build AI, meta. What about mentoring? How does that change when AI can write code?
Mentoring becomes less about teaching syntax and more about teaching critical thinking, right? The focus shifts to helping junior engineers develop discernment, how to question the code AI generates, how to understand the why behind it, fostering that productive struggle to build deep intuition rather than just copy-pasting an AI's answer, and encouraging reciprocal mentorship too. Juniors often know the latest AI tools better. They can teach seniors. It has to be a two-way street.
Building intuition, not just taking answers. I like that.
Yeah.
And the team culture.
The high-performance culture doesn't happen by accident. You have to engineer it too. Often, it revolves around a tight feedback loop, like the assess, parallelize, optimize, deploy APOD cycle. Constant measurement, constant improvement. And foundational practices are key. Rigorous version control for everything: models, data, code, configs. Continuous evaluation frameworks to catch regressions. High standards for code quality and documentation. It's about building a reliable, repeatable process for innovation.
Engineering the team as much as the tech. Okay, so looking at everything we've discussed, where's this all heading? What's next on the horizon for high-performance LLM inference?
We're seeing a few big trends emerge. One is definitely the ascendancy of mixture of experts MOE models like Mistral and others. They offer a path to much larger model capacity and capability without a proportional jump in the compute needed for inference, because you only activate a fraction of the model for each token. But they bring new systems challenges, managing VRAM for all those experts, efficient expert parallelism and routing.
More complex models, new scaling challenges, what else?
We're also seeing a proliferation of specialized hardware accelerators. It's not just NVIDIA GPUs anymore. We're seeing new chip architectures, startups designing hardware specifically for transformer workloads, maybe even hardware-first designs focused on extreme efficiency, especially for running models on edge devices. The hardware landscape is getting more diverse.
More options, maybe more complexity in choosing the right tool. And any other big ones?
I think we'll see the maturation of speculative decoding. It's moving from a cool research idea to becoming a standard feature in serving frameworks. We'll likely see more sophisticated draft models better integration, making that lossless speed up just part of the standard toolkit. He really embodies that asymmetric compute principle, which I think we'll see applied in more ways. So yeah, the big picture trend seems to be the future of LLM inference is going to be increasingly sparse, with MOE increasingly specialized with hardware choices, and definitely distributed with architectures like disaggregation.
Sparse, specialized, and distributed. It's a great summary. Wow, what an incredible journey through LLM inference systems today. We went from the basic building blocks, that crucial prefill decode split, through all those layers of optimization, batching, scheduling, KV cache magic, quantization, speculative decoding, then into scaling with parallelism, disaggregation, all the way to the future trends. So here's your mission, should you choose to accept it. As these AI systems get ever more complex, more decentralized, with all these specialized parts and distributed workflows, how do you think the skills of a, let's say, traditional software engineer need to change to really thrive in this new world? Something to ponder. Thank you so much for joining us on this deep dive.